Assalamu alaikum and hello everyone. Today, we continue with other methods that can be used to identify lyotropic liquid crystal phase. In my previous lecture, I have explained that there are two methods in determining the phase of lyotropic liquid crystals by optical polarizing microscopy. The first method is called contact penetration study, in which we can find out what lyotropic phase exists, but this method cannot find out the actual composition of the solvent or mesogen. The second method is to prepare a sample by knowing the composition of each component accurately. For differential scanning calorimetry, nuclear magnetic resonance and X-ray analysis methods, we have to study samples whose composition is known accurately. Once the liquid crystal region was identified based on the contact penetration study, the formulations at desired component ratios can be prepared. The preparation of the liquid crystalline material will be added to the required weight of water, or any solvent, and mixed thoroughly to form homogeneous lyotropic liquid crystal phase. The resulting formulations must be tightly sealed and stored for 1 week before investigation, and their physical stability can be studied by observing periodically the occurrence of phase separation. Differential scanning calorimetry, DSC, is a technique in which the difference in the amount of heat required to increase the temperature of a sample and reference are measured as a function of temperature. Both the sample and reference are maintained at nearly the same temperature throughout the experiment. For DSC measurement, samples in about 5 to 10 milligrams is required in aluminium pans and immediately sealed by press. The reference will be the empty pan. The samples were cooled at a heating rate of -5 degrees Celsius per minute to -40 degrees Celsius. Kept the sample at -2 minutes at 40 degrees Celsius temperature, and before heating the sample to the temperature range that required. When melting or freezing transition occurs, sample pan is cooler or hotter than reference. Therefore, the instrument needs to supply different heat to keep temperatures the same. The difference allows heat, the delta enthalpy and temperature of transition, to be measured. DSC is more accurate to assign the transition temperature and to confirm the phase change, but no information on type of phases. Except, it is very useful to distinguish gel phases from crystals. The typically delta enthalpy for gel melting is almost half of that delta enthalpy of crystal melting. Gel phase usually melts to lamellar but not always. Mesophase melting transition enthalpies is small. Typically 10% of delta enthalpy of crystal melting. Based on the enthalpy change value, no difference between lamellar, hexagonal, or cubic phases. Considering the formation and structure of lyotropic liquid crystals, it can be stated that one of the principal components of these surfactant-based systems is water. Different forms of water have been detected in surfactant-based microstructures such as microemulsions and liquid crystalline phases. Water can be divided into two categories: free and bound water. The part of water which achieves complete freezing is termed free water, and the remaining unfrozen water is termed bound water. Please refer to the diagram on the slide for better illustration. When the system is sufficiently diluted, free water is present in it, which is assumed to have similar physico-chemical properties like pure water. Its presence can be detected by so-called sub-zero temperature differential scanning calorimetry by the appearance of the melting peak on the DSC thermogram at about 0 degrees Celsius. The disappearance of the melting enthalpy of water, at the disappearance of free water, coincides with phase changes occurring in the liquid crystalline structure. The knowledge of the proportion of varying types of water is important to get information of the structure, which has a strong effect on drug release from pharmaceutical formulations. On the left side of the slide shows the DSC thermograms of a water-saturated polycaprolactone, PCl, sample. First, dry sample DSC, 100% PCl, was conducted as a control group. In pure PCl exhibited sharp and single melting and crystallization transitions. However, phase separation was observed with 50%, 70%, and 80% PCl in the network system. At low PCl content, the crystallization peak disappears. Noticeably, a water crystallization peak in the cooling trace at 20 degrees Celsius gradually grows with decreasing PCl content, indicating the hydrophilicity is increasing. Besides the water crystallization, hydrogels containing more than 50% PCl are able to maintain the PCl crystallization peaks as well in the cooling cycle. The disappearance of PCl crystallization peaks indicate hydrogels with less than 50% PCl cannot crystallize or possibly merge with the water crystallization peak below room temperature. Although two distinct water melting peaks around 0 degrees Celsius and -20 degrees Celsius are observed, only one sharp water crystallization peak appears in the cooling trace. According to the classification of three forms of water in the polymer, free water melts at 0 degrees Celsius and a water melting peak at -20 degrees Celsius is attributed to freezable bound water. Melting temperature of freezable bound water is usually lower than bulk water due to hydrogen bonding, but changes slightly or remains constant with different in sample and water mixtures. In some cases, a cold crystallization peak appears on the heating cycle for an intermediate water concentration range. That is mainly due to some water molecules unable to crystallize completely, yielding a higher fraction of water molecules that are non-freezable under the experimental condition. DSC is powerful and accurately determine the phase transition behavior and molecular mobility during the interaction between water and liquid crystalline molecules. DSC also able to detect gel to liquid crystalline phase. The diagram on the slide shows the transition temperatures of dipalmitoyl phosphatidylcholine, DPPC, in water system. There are two transition temperatures can be observed. The first transition, with small enthalpy change occurs at 36 degrees Celsius is the transition of solid DPPC to ripple layers. This kind of transition doesn't require much energy. The second transition is belong to the gel to liquid crystalline transition. Larger energy required for this transition, for melting the chain to make it fluid layer, which is the lamellar phase. Lamellar phase form over a certain range of concentration and above certain characteristic temperature, gel to liquid crystalline temperature. Below gel to liquid crystalline temperature the surfactants are poorly soluble in water and thus cannot at least spontaneously assemble as nanostructures. At the phase transition temperature there will be a large increase in heat absorption as the liquid changes from gel phase to liquid crystalline phase. See the diagram on molecular dynamics simulations of dipalmitoyl phosphatidylcholine to see the chain melted after the gel to liquid crystalline temperature. The gel phase or the sponge phase is the L-beta and the tilted gel phase is L-beta prime. The simulation pictures on the bottom is the lamellar layer phase, L-alpha. In nuclear magnetic resonance, we can use proton or deuterium NMR to study the liquid crystalline behavior. In proton NMR, the phase characterization will be based on time constant, T2. T2 relaxation is the process by which the transverse components of magnetization, MXY, decay or dephase. As originally described by Felix Bloch, 1946, T2 relaxation is considered to follow first-order kinetics, resulting in a simple exponential decay, like a radioisotope, with time constant T2. Thus T2 is the time required for the transverse magnetization to fall to approximately 37%, 1/e, of its initial value. Synonyms for T2 relaxation are transverse relaxation and spin-spin relaxation. The time T2, in unit of microsecond in related phase is provided on the slide. For deuterium NMR, the phase identification is based on quadrupole splitting. Deuterium NMR spectra has allowed us to definitively locate and characterize the region where two liquid crystalline phases coexist. Arise with nuclei having spin quantum no I greater than or equal to 1. This applies to deuterium, nitrogen 14, sodium 23 and chlorine 35. Nuclei with I greater than or equal to 1 have electric quadrupole moment, interact with non-zero electric fields. For isotropic phase, motion averages effect to 0. For birefringent phase, the deuterium NMR line split into two I peaks. Quadrupolar splitting, delta V, for deuterium, with I equals 1, the resonance split into two I, therefore two peaks observed. Deuterium nuclear magnetic resonance spectroscopy has proven to be an important technique for the characterization of the liquid crystal's phase because the deuterium NMR quadrupolar splitting is proportional to the local orientational order parameter. Refer to the equation on the slide. These are the characteristic NMR spectra and phase. 1 for isotropic phases such as micelles, cubic and sponge phases 1 observes a narrow singlet. 2 for a single anisotropic phase, such as hexagonal or lamellar structures, a doublet is obtained. The magnitude of the splitting depends on the type of liquid crystalline phase, which is twice as much for the lamellar phase than for the hexagonal phase. 3. The third spectrum shows that two phases are coexist. For the fourth spectra also shows two phases coexist. Lamellar and hexagonal coexist. Two doublets are observed. 5. The fifth spectra shows three phases coexist. Three phases region with two anisotropic phases belong to lamellar and hexagonal and one isotropic phase, one observes two doublets and one singlet. In deuterium NMR study, the peaks does not provide information on whether the microstructure is of the normal or reversed type. Normal and reversed phases are easily distinguished using conductivity measurements. For normal phases, which are water-rich, the conductivity is high. In contrast, for reversed phases, which are water-poor, the conductivity is much lower, by several orders of magnitude.
What do you know about X-rays? We all know they are used to take pictures of your bones or see the contents of your bag at the airport. But have you ever imagined that a very powerful source of X-rays could also help solve industrial problems and could help speed up your innovation process? Well, yes it can, and the ESRF does this. A wide range of techniques is open to industry at the ESRF. Dr. Michal Stutzki, beamline scientist, will give us an insight into small and wide-angle X-ray scattering, also called SACs and WACs.
Typical samples which can be investigated with small angle and wide angle scattering techniques are present in everyday life. As you can see here, the products on the screen. All these products contain colloids, proteins, polymers or surfactants. And the final self-assembly of these building blocks into, for example, micelles or vesicles determines strongly the conformation of the final product. The investigation of vesicles is important for cosmetics, for detergent formulations, but also for pharmaceutics as drug carriers. General applications for small angle and wide angle X-ray scattering are in the field of soft condensed matter, non-crystalline structural biology, and interdisciplinary areas of soft matter biology and nanoscience. Looking especially at the field of proprietary research, the combined small angle wide angle scattering is a powerful method to determine the nanostructure and phase behavior of multi-component systems involved in cosmetics, in detergents, pharmaceuticals, and also polymers. In addition, in situ studies can be performed under similar conditions as that involved in industrial processing. And typical industries which are interested at beam time at the ESRF are from pharmaceutical industry, detergent companies, personal care product manufacturers, polymer industry, food industry, but also for medical diagnostics. Using the high brilliance small angle and wide angle X-ray scattering setup at the ESRF has several advantages. This, for example, is the high photon flux and the reduced divergence of the beamline for high resolution measurements over a wide range of length scales from a few angstrom to the micron scale. It's also the high dynamic range and the millisecond range time resolution available, and the adapted sample environments we provided our beamline, ranging from rapid mixing devices, thermostated environments to magnetic fields. Also, the expertise for data analysis is present in place. Looking at microbeam, small angle and wide angle scattering, in this case the X-ray beam is focused on the sample, allowing micron and nanometer spatial resolution directly on the specimen. For testing, for example, local nanostructure of very small objects, but also deducing highly localized information by scanning thin specimens with micro and nanometer real space resolution. Small and wide angle X-ray scattering is a well-established technique to probe the nano to micron scale structure of soft matter. In this technique, a monochromatic X-ray beam falls onto a sample where it's scattered by spatial fluctuations of the electron density within the material. The scattered intensity after passing through a evacuated flight tube is detected with a two-dimensional CCD detector. As samples can serve, for example, polymer pieces of a few millimeter size, a drop of gel, or also solutions from 15 microliter. The scattered intensity recorded in the 2D detector is first azimutally averaged, and the scattered intensity in absolute units as a function of the scattering angle can be afterwards fitted to structural models, which helps them to distinguish between different morphologies, for example, spheres, micelles, or vesicles. An example for using high brilliance combined small angle and wide angle X-ray scattering is a study of a dilute unilamellar vesicle system, as it's often present in fabric conditioner. Typical of such a system is the transition from a liquid crystalline state to a gel state as a function of temperature. And there's a big interest to move this transition temperature down to low temperatures for high performance of the fabric conditioner. In this graph you see a combined small angle and wide angle X-ray scattering study measured at two different temperatures. It's very interesting to look now at the wide angle scattering signal at one temperature, comparing the background scattering with the sample scattering, and you see there's only a very tiny difference between the two curves. However, the high detection limit we have available at our beamline allows to clearly distinguish between the two different conformations measured at 35 and 60 degrees. We can clearly determine the structure within the unilamellar vesicles. In one case, the liquid crystalline state, in the other case, the gel state. The second example investigates the local nanostructure of Kevlar fibers by microbeam small angle X-ray scattering. The Kevlar fiber was cut into a small specimen of about 10 micrometer thickness and investigated on axis. This means directly studying the cross-section of the fiber. The 2D image seen here shows the orientation of the local nanostructure within the fiber, and you can clearly see the skin core morphology of these high-performance fibers. Looking more closely at single scattering images, for example at point 1 in the center, you see an isotropic scattering pattern which is indicative of a random orientation. Whereas in the skin you see an oriented image in figure 3 which indicates the orientation. The use of small angle and wide angle X-ray scattering at the ESF will help you to speed up your research and development by studying the internal structure of your specimen.
If you're interested to know more, or to find out how the ESRF can help your business, please contact Dr. Edward Mitchell, our Business Development Manager, or visit our website.
X-ray analysis is the most qualitative techniques for identification of the various liquid crystalline phases. It is based on diffraction studies, either light, X-ray, or neutron. Liquid crystalline structures have a repetitive arrangement of aggregates, and observation of a diffraction pattern can give evidence of long-range order and so distinguish between alternative structures. This can be used to study the extent of translational or positional order, and thus infer the type of liquid crystal phase. Each mesophase has different diffraction pattern, can identify type from sequence of lines as summaries in table on the slide. Problem arise if only one or two lines observed. With that minimum peaks, we cannot assign structure without another method, because all kind of phases will have this ratio. Beside that, multiple phase samples will show overlapping patterns. Deuterium NMR will be the best tools that solve that problem. Another limitation with X-ray analysis is, this instrument will not able to provide the exact transition temperature. From page 14 to 17 is the summary on phase, diffraction image, and the plot of intensity versus X-ray scattering vector for lyotropic mesophases. These are the summary of spacings formulae and space groups for lyotropic mesophases. Each method has advantages and disadvantages. Therefore, it is important to confirm the liquid phase present by using several complementary techniques. This slide shows the use of 3 different techniques for the phase identification. Images C and D from the optical polarizing microscope do not show a clear image of the lamellar phase, but we can confidently state that it is a lamellar phase when the phase is confirmed by the results from the SAXS analysis. The same goes for the hexagonal phase. Since the F and G microscope images are not clear, findings from the SAXS analysis have concluded the type of phase. The thermogram from the DSC findings does not show the type of phase, but it can tell that there is one liquid crystal phase exist. There were 2 transition temperatures observed. The transition temperatures are for the melting point and the clearing point.